Okay, so this is problem 2 from homework 3. And the problem asks you to do what? So the problem, you're given two variables, r and theta. R we know is Rayleigh distributed, which has this PDF given here, and this PDF given here. And we know that theta is uniformly distributed. And moreover, theta and r are independent of each other. And then we have two additional variables, which is x equals r times cosine theta, and y, which is y r times sine theta. And then we're required to prove that x and y, both of them, are Gaussian, identical with zero mean and variance sigma squared. And more importantly, we are also required to prove that they are independent of each other. Okay. Now, there's a slight bit of an error, if you will, in the hint that's given to you, which says that to show independence between x and y, all you need to do is to show that x and y are uncorrelated. We're going to see in a bit that this is not strictly true, so we'd have to resort to some other way of doing it. Nevertheless, the way I'm going to start out with is the first thing I'm going to do is I'm going to try to prove that x is Gaussian with zero mean and variance a squared, and y follows the same distribution. And then I'm gonna have that discussion about independence between x and y. The first thing I'm going to show is that x and y indeed turn out to be uncorrelated, but then we're going to debate whether that uncorrelatedness is enough to prove independence or not. And I'm going to try to argue that that's not enough. So that means we need something else to show independence. So here we go. Right. So this is so the first thing we want to do is that we're given x equals r cosine theta. So we're given x equals r cosine theta, and we're given y equals r sine theta. And let me just focus on x first. The solution for y is very, very similar. So in order to compute the PDF of x, the first thing we do, as we've done in class, is to compute the CDF of x first, right? So I'm going to compute the CDF of x evaluated at z. The reason why I'm using z and not x here, that's going to become clear in just a bit. So this is just the probability that x is less than equal to the variable small z. But since the random variable capital X is r times cosine theta, that probability is just simply equal to the probability that r times cosine theta is less than equal to z. Now, computing this probability just entails what? Integrating the joint PDF of r and theta over the region which corresponds to this condition, r times cosine theta is less than equal to z. So therefore, this is the double integral over the joint PDF of r and theta over what? Over the region that r cosine theta is less than equal to z. And what do I integrate? I integrate the joint PDF of r and theta, but since they're independent, the joint PDF is just simply the product of the two PDFs, right? So this is r over a squared e raised to power minus r squared divided by 2a squared times u of r. So this is the PDF of r, and times 1 upon 2 pi, and this is dr d theta. In order to evaluate this integral, I am going to use change of coordinates. So this, you can see this is polar coordinates. If I can go from polar to rectangular, so polar to rectangular. So this is what I'm going to do. Right. So for going from polar to rectangular, I know that x is another variable which is equal to r cosine theta. Let me use that. And y equals r times sine theta. And this is the reason why I did not use x, so that I can use x for the x coordinate in the rectangular coordinate system. And that I believe, I mean, that's easy to understand. If I had used another instead of x, something else, that may have confused people. So if x is r cosine theta, y equals r sine theta, I know that r squared is equal to x squared plus y squared. And moreover, I know that r times dr times d theta is equal to dx times dy, right? Now, based on this, I can just lump these things together. R times dr times d theta is nothing but dx times dy. Because of which the joint, the CDF of x is this double integral, and this is 1 upon a squared e raised to power minus r squared by 2 a squared times 1 upon 2 pi, and the r times d theta is nothing but dx and dy, and the condition that r cosine theta is less than equal to z is just the condition that x is less than equal to z, and therefore x must be from minus infinity, it must be integrated from minus infinity all the way up to z, and y is of course from all the way from minus infinity to plus infinity. So this is an integral that we need to solve, which becomes not too difficult. It's quite easy, in fact. And actually, so r squared, remember, is x squared plus y squared, right? So this is x squared plus y squared by 2a squared. Now, x and y, turns out I can separate them out. So here I can have the integral over y from minus infinity to plus infinity. And this is 1 upon root 2 pi times a squared. So I'm skipping a step here. So 2 pi is just root 2 pi times root 2 pi. So I'm going to separate them out as two separate terms inside each integral. So this is e raised to power minus y squared divided by 2a squared times dy. And times I have another integral which is from minus infinity to z. And this integral is, of course, over x. This is 1 upon 2 root 2 pi a squared. And this is e raised to power minus x squared by 2a squared times dx. And clearly this integral is equal to 1 because this is nothing but the area under the curve of a valid Gaussian PDF, which is zero mean, and a variance a squared. So this thing, of course, is equal to 1. Now, so what we're left with is that the PDF or the CDF, sorry, of x is in fact equal to the integral from minus infinity to z. And what are you integrating? You're integrating this thing here, which is 2 pi a squared e raised to power minus x squared divided by 2a squared times dx. And it's clear that the PDF, because CDF is nothing but the integral of the PDF from minus infinity to the point where you're evaluating the CDF, and that point is z. So therefore, the CDF or the PDF is nothing which is inside the integral, right? So this is the PDF. So this is the PDF of x, right? And you could do another way. You could just integrate the CDF with respect to, so differentiate the PDF with respect to z, and you're going to get the same result. And so therefore, this turns out to be equal to, so this implies that the PDF of x evaluated at z is equal to 1 upon root 2 pi a squared e raised to power minus x squared divided by 2a squared, right? So this is the, so this is z, sorry. And if that's confusing, I can just use x, right? So z is just a variable. I'll use z, x instead of z now. This is e raised to power minus x squared divided by 2a squared. And it's clear that we've been able to show that x is indeed Gaussian, which has a zero mean and has a variance a squared, right? So that's what our conclusion is. Now, using the same methodology, it's very, very easy to show the same methodology. So easy to show that y turns out to be Gaussian as well. And you follow the same principles. I mean, you follow the same integral. Instead of just integrating or differentiating over x, you're just going to be differentiating over y. You're going to find that y also turns out to be Gaussian, which is a zero mean Gaussian random variable and has a variance sigma squared. Okay, so we've been able to show that x and y are marginally Gaussian. Each one of them, the marginal distributions are Gaussian indeed, and they're identically distributed. What we want to do next is to try to show that they're independent as well. X and y are independent as well. Now, as the hint indicated, so that's what I'm going to do next, is just to compute the correlation, right? So let's just do it for compute the correlation, and then I'm going to make some comments with regards to whether that's a good indicator of independence or not. Okay, so we compute the correlation or the covariance, in fact. So let's compute the covariance between x and y, right? So that is the CXY is nothing but the correlation. And the reason why it is the same as correlation is because X and Y, both of them, we found them to be zero mean, right? So this is the expected value of XY, which is the covariance. And this is equal to R cosine theta. X is R cosine theta. Y is R sine theta. And this is nothing but expected value of R squared times cosine theta times sine theta, and just using some trigonometric identity, which is this is expected value of half times r squared sine 2 theta. And then we know that r and theta are independent, right? So if they're independent, I can say the covariance between x and y is just simply equal to half expected value of r squared times the expected value of sine 2 theta. And then it's quite easy to show that this turns out to be equal to 0 because theta is uniformly distributed. You're integrating sine 2 theta over 0 to 2 pi, and the area under the curve is going to be equal to 0. So this turns out to be 0, right? So that means x and y, they are uncorrelated, right? So that's what we've been able to show, right? So x and y are uncorrelated, and there's an additional thing that we know, I mean, from before, which is we know that x and y are Gaussian as well. We know that x is Gaussian, right, and y is Gaussian, right? The question here is the uncorrelatedness enough to prove independence, right? So is the uncorrelatedness, if that's a word, I don't know, enough, strictly speaking, to prove independence? And the first thought that actually comes to mind is, which came to my mind as well, yes, that should be enough because x is Gaussian, y is Gaussian, and we know that if the random variables are Gaussian, and if they're uncorrelated, they must be independent as well. But a little deeper thought reveals that that may not necessarily be true, right? So the actual, when we say Gaussian random variables are uncorrelated, means they are independent as well. That applies to the case when x and y are jointly Gaussian, right? So that's a clear distinction here that we should be clear about, right? So if x and y are jointly Gaussian, then if they're uncorrelated, they must be independent as well. That's a fact that we've been able to establish in our class discussions, okay? What it does not imply is if x and y are marginally Gaussian, this does not necessarily mean that x and y must be jointly Gaussian as well. And I can actually give you counterexamples. The way I was able to think about this more is to think about counterexamples where x and y are marginally Gaussians, yet they are not jointly Gaussian. And that was a counterexample in which they were uncorrelated, yet they were not independent, okay? So for x and y to be, for uncorrelatedness to imply independence, we need to show that they're jointly Gaussian as well. In other words, the joint PDF satisfies the joint Gaussian distribution. Okay, so this clearly, therefore, is not enough. And think about the counterexample, though. So that's something I leave that off as an exercise, something to think about. So the conclusion is, okay, we need to do something else to show independence. We would actually need to compute the joint PDF and show that the joint PDF in fact turns out to be equal to the product of the marginal PDFs. To show independence, we have no choice but to compute we must compute the joint PDF. So that's what we're going to try to do next. So we must compute the joint PDF. Okay. Now, how do you compute the joint PDF? It turns out there's a separate section in the textbook which I told you earlier as well. There's formulas there. I mean, there's working which leads up to a relationship between the joint PDF of r and theta with the joint PDF x and y through a Jacobian. But since we have not explicitly discussed that in class, I am not going to go there. Instead, I'm just going to focus on the fundamentals, the basics that you could use to prove what we require to prove without using the Jacobian operator, okay, without using the Jacobian. And the way I'm going to go about this, as I said earlier, through the fundamentals. So I am going to compute the joint CDF of x and y, and then I'm going to differentiate that with respect to x and with respect to y, and then I'm going to show and whatever I get is the joint PDF. Okay, so let's compute the joint PDF, joint CDF evaluated at Z1 and Z2. Once again, the reason why I'm using Z1, Z2 is because we're going to have to go from polar to rectangular, and I'm going to use x and y for the rectangular coordinate system, right? So this is the probability that x is less than equal to Z1 and y is less than equal to Z2. And this is, of course, the probability that r cosine theta is less than equal to Z1, jointly the event with r sine theta is less than equal to Z2. And in order to compute the probability, once again, I'd have to integrate the joint PDF of r and theta, but since they're independent, there's just a multiplication, the product of the PDFs. So this is 1 upon, so this is r upon a squared e raised to power minus r squared divided by 2a squared times ur. So this is the PDF of r. This is the PDF of theta. Of course, this is between 0 and 2 pi. And then I'm integrating over dr and d theta. What is the region that I'm integrating over? The region that I'm integrating over must satisfy r cosine theta being less than equal to Z1 and r sine theta being less than equal to Z2. So this is what I need to integrate over. And once again, as we've done earlier, I am going to go from polar, once again, to rectangular coordinate system, right? And I'm going to skip steps. This is very, very similar to what we've done earlier. So this is evaluated, the joint CDF evaluated Z1 and Z2 is this double integral of what? 1 upon a squared e raised to power minus r squared by 2a squared times 1 upon 2 pi times dx and dy, and x, which is r times cosine theta. Remember this, so this thing here is x, this thing here is y, and therefore the integral over x actually goes from minus infinity to z1. Integral over y goes from minus infinity to z2, and of course this is r squared is x squared plus y squared to sigma squared, and there's a bracket here. Okay. And once again, we see that the integrals are separable, and that makes our life a lot easier. So this is integral from minus infinity to z2. This is 1 upon root 2 pi a squared e raised to power minus y squared by 2a squared times dy, and times integral from minus infinity to z1, 1 upon root 2 pi a squared e raised to power minus x squared by 2a squared times dx. And once again, it's clear that's actually a product of two CDFs, and which are actually Gaussian CDFs. Okay, so clear that this is Gaussian and this is Gaussian as well, because of which if I take the partial derivative Okay, so this is correct way of doing this would have been, okay, what you do is you compute the partial derivative of, so the fxy evaluated at z1 and z2 is the derivative with respect to z1, derivative with respect to z2 of what? The CDF, right? And this would have turned out to be equal to 1 upon root 2 pi a squared e raised to power minus z1 squared by 2a squared multiplied by 2 pi a squared e raised to power minus z2 squared by 2a squared. And this now is enough to show, and this actually, this one equation that you see here, this one equation that you see here, which computes the joint PDF of x and y, this is enough to conclude the following. This is enough to conclude the following, that x is Gaussian, which has a zero mean and variance a squared. Similarly, this is enough to conclude that y is also Gaussian, with a zero mean and variance sigma squared. And this is also enough to conclude that x and y are independent. Why? Because their joint PDFs are equal to the product of the marginal PDFs. So, I mean, if you were computing the solution, this thing that you see on your screen, um, this would have actually been enough. Yeah. Okay. Yeah. So this would have been enough to this is the complete solution for the problem given.